Can you guys see my screen? Yes, no, maybe so? We good? Alright, we good. Okay, so today we are talking about greedy algorithms, which, even though the name sounds really stupid, honestly speaking, they are actually very useful algorithms. So, let us talk about what the heck they are. So essentially, what a greedy algorithm is literally just pick the best option right now and hope that it turns out better in the end, okay? Now honestly, in real life, this is a pretty bad idea, right? Just because you play video games for 2 hours does not mean that you're going to be happy later on, but in this type of algorithm, it actually kind of works. So let me explain. Let's say that you want to get the maximal number of cookies, right? Like every day at the store, there are CT cookies at the store. And you can carry a maximum number of X cookies per day. So if you look at this example, 1 cookie is available on day 1, 2 on day 2, 4 on day 3, and you can take 1 on day 1, 2 on day 2, and 3 for a total of 6 cookies, right? So could anybody tell me what the optimal way to take home cookies is? Like each day, how many cookies should you take home in order to maximize the number of cookies you get? Anybody? It's not a hard...
All of them?
Say it again?
All of them?
Yeah, just take as many as you could each day. It literally does not impact your later days to take more cookies today. Always just take the max number of cookies that you could take today, and you will have the maximum number of cookies overall, right? Another example, let's say we're trying to split a string into a balanced string. So basically a balanced string is where you have like an equal number of L's and R's. So essentially for this example, you see RL, that's a balanced string, RLL is a balanced string, RL and RL are both balanced strings. So how do we do this like quickly? We want to break it up into as many chunks as possible. So how do we do this?
You just like find a string where the amount of R's and the amount of L's are equal, and then you just separate that string and keep going.
Yeah, so as soon as you find a balanced string, you just split it off, right? There's no reason to not split it off because, like, once a string is balanced, like, to add more to it, like, okay, so let's say you have a balanced string and you make it into a bigger balanced string. That's the same thing as splitting it into two balanced strings. There's literally no reason not to cut off that first balanced string. So essentially the idea is, in a greedy algorithm, just not worrying about the future, just focusing on what you have now and just doing the best thing right now is going to eventually lead you to the best solution. So if we find the shortest, so as soon as we see a balanced string, we just split it off and we end up with the largest amount of total substrings. It's pretty good. So here's a little bit more of a practical application, right? Because honestly speaking, it's kind of common sense that if you go to a cookie store, the best way to take the most cookies is just to take as many cookies as you can. But here is another example, okay? So let us say that you're a really busy guy and you want to make sure that you don't have any overlapping activities, but you want to have as many activities in your day as possible, right? Like each activity starts at 0, ends at 6, starts at 1, ends at 4, and you want to choose the biggest number of these that do not overlap. So just looking at the data, does anybody know what the answer is? Like, what's the biggest number of activities we can do?
3?
Yep, 3. And which, give me like an example of which 3 activities we can do.
B, E, and then H.
Yep. Apparently, and in this case, like that's not even obvious. Just for a human, like obviously we could do it, right? But even for a human, this is not super obvious. So how can we do this greedily, right? So the first thing you might think is, why don't we just take the one with the earliest start time? Let's just start with that first guy, right? So we take A, so that eliminates all of these guys all the way up till G, and then we take G, but god dang it, that's only 2. What? That sucks. So, does anybody have another idea of how we can do this better?
Find which one ends the earliest.
Yeah, exactly. And could you like give me a reasoning for that? Why is ending earlier better?
Because then you can start the next activity earlier.
Yeah, basically the idea is if you end earlier, you're eliminating fewer of the later activities, right? Like A is literally eliminating all these guys. That's kind of lame, right? But if you look at B, it's only eliminating the first 4. So essentially, the one that ends earliest is going to eliminate the fewest number of activities. So basically, all we got to do is sort it by end time, and we're good. Wait, hold up. Let me just assign a delay, because in delay, come on, you can't come so late. No, I'm kidding. Hold up.
I was literally held hostage till like 1 minute ago.
Okay, give me a sec. I think I need to. Okay, there we go. Let me assign you. Where are you? Who are you held hostage by?
stream.
Of course. Alright. Have fun. Okay. So, anybody, tell me which is the first guy we're gonna take. Like, who has the earliest end time? Which of these boys have the earliest end time?
B.
Yep, B, so we take B, alright. And then, next, which one has the earliest end time after B? Yeah, well, I mean, you jumped a step ahead of me, but basically the next one is C, but we can't take C because, like, it's already overlapping. Then we look at E, because E is the next one that ends, right? And we could take E, right? It doesn't overlap with B. So we go to E. Now we look at F, or no, which is the, yeah, we look at D now, right? Actually, sorry. We look at F, right? And basically, F is still overlapping. We look at G. G is still overlapping. And finally, we end up with H. H is the earliest endpoint that does not overlap, and hooray, we got our 3 scheduled things that are going to work, okay? So, essentially, what I'm going to do is we're going to live code this for you guys real quick, and you guys are going to tell me what to do, because this should be a really fast code up. So, let's see if you guys remember. We're going to use Python, because Python is the best language in the universe. Exactly. Alright, so, what is the first step? We got to first read in our input. That's kind of obvious, so I will do that, but can anybody tell me what the next step after we read in our input is? Anybody? What is the first thing we gotta do? Come on, people. Anybody?
You run through this, the end time, and then find the smallest thing.
Well, first you gotta do something to make sure it's in an order that we want it, right?
Sort it.
Yes, we had to sort it first, and what do we have to sort it by?
End time.
Yes, we had to sort it by end time. Very nice. Okay, so give me a second. Alright, this should work, right? Do I have the right number? Oh, I don't have the right number of parentheses. There we go. Okay, so now we've read in all our activities, and now we gotta sort it. So, essentially, to sort in Python, you do activities.sort, and then we want to sort by the second thing. So essentially the way you do that in Python is you do t is equal to lambda x x1. Okay. So now if we print out our activities, we would get, sorry, yeah, just print out activities. Okay, so now let's try running this and use our input example. God dang it. Okay, hold it. So we run it. Okay, so our first thing is 8, and let's put this side by side. Holy moly, I'm lagging. Okay, so our input is 8, 0, 6, then we got 1, 4, then we got 3, 5, then we got 4, 7, then we got 5, 9, then we got 6, 10, then we got 8, 11. Okay. And did I miss something? Oh, I did miss something. Which one did I miss, people? Oh, I missed D. Oops, 3, 8. Okay. Alright, so you can see, right? It ordered it 4, 5, 6, 7, 8, 9.
We can't see that.
Oh, shoot, yeah, sorry. Okay, let me just put it back in. Alright. Now you guys can see it. So you can see, right? Basically, we have, okay, there we go. So basically, you see the second one is now in order. The end time is in order 4, 5, 6, 7, 8, 9, 10, 11. Very nice. Okay, so now what is the next step? Anybody? Por favor, what is the next step? We have it sorted. Now what do we got to do? Did you say something, Samuel?
And the start time that's like right after the end time.
Yeah, so essentially we need to keep track of our end time, right? Because we had to know where our end time is, so we could choose something that's after that end time. So we're going to start with our end time being 0, right? Because anything after 0 is fine. And we also had to keep track of how many activities we have right now. So right now we have 0 activities, and now we loop through it, okay? So we do for activity and activities, oh my god, okay, in activities, for each one. So what do we do with each activity? When do we add it to our list?
If it has like the smallest end time and doesn't overlap with the previous one?
Well, we already have the smallest end time, right? Because we're going from lowest end. We already sorted it, and we're just going from beginning to end, right? So all we got to do is check that it does not overlap with what we already took. So the way we do that is if our start time, which is activity 0, is greater than, oops, that's not how you type it, 0. Activity 0 is greater than or equal to end time, then we have to add it to our list, right? So now we can do num plus equals 1. You can't do plus in Python, which is the one bad thing about Python. And then what else do we got to do? Now, what else do we got to do? This is a good question.
We have to change the end time.
Yep, we change the end time to the end time of this activity. Activity 1. Okay. And why don't we just make this interesting? Let's just keep track of best activity. All right. And we'll just store it in a list, and we'll just put it in over here. So best activities dot pen activity. All right. And we could take out the num, honestly. We could just look at the length of our list. Okay. And at the very end, all we got to do is print best activities. And let us try running this guy. So our best activities 1, 4, 4, 7, 8, 11. Very nice. We coded it up thanks to you guys. Okay, very nice. Let us continue the presentation. Oops, I stopped sharing screen. That was small brain. Hold up. Okay. And okay. Moment. There we go. Okay, so when does the greedy algorithm fail? So a really good example of this is like chess, right? Like literally so taking a piece, right? Like if I take the other guy's queen, even though my king is in checkmate, that's not a very smart idea, right? Like I might be getting the most value for that turn, but I'm not like actually winning the game, right? So that's one example where a greedy algorithm doesn't make any sense. Another example is like knapsack. Is basically the idea of knapsack is you want to take as many items that fit in your bag, but like you also get the most award for it, right? But the only thing is, like, what happens if you take a really big item that gives you a ton of value, but then you don't have space enough for like some other like slightly smaller thing that has like almost as much value, right? Like just taking the thing with the highest value is not the best option because you want to consider a lot of different things. So that is another example. Could anybody else think of another example? I'm trying to think of something else, but anybody have ideas? What's another good example of something that doesn't work with greedy? Let's see.
What about Deitres?
Well, okay, so that's a good point. Deitres is a greedy algorithm, but if you have negative edge lengths, right? Let's say you have negative edge lengths in a graph. Like let's say if you take a road, you could go backward in time, right? Then even if you take the longer road now, there might be a road later on that like takes you back in time, and you might end up taking a shorter path by doing that, right? So essentially the idea is that's where a greedy algorithm would fail. But in a normal universe where you can't go backward in time, a greedy algorithm actually works, which is what we're going to talk about now. So the first thing we got to talk about is Deitres' algorithm, which is unfortunately, Samuel, a greedy algorithm that we were actually planning on talking about. So essentially what it lets us do is it allows us to find the shortest path between two vertices of a graph. And basically the idea is that, like, let's say that I want to get from point A to point B, okay? And there's a point C in the middle. Then to get to point B, if point C is in the middle, I want to take the shortest path to point C too, right? Like, let's say there's two paths to C. Why the heck would you take the longer path to get to C, when you can easily take the shorter path to C and then get an even shorter path to B, right? So essentially every single path, like getting to B, like from A to B, those are all the shortest paths. So that's basically the premise right here. So essentially how it works is you start from vertex A, and let's say we wanted to find the shortest path to like all the other guys, right? So essentially what we want to do is we want to keep finding shortest path. There's no reason to find a longer path because that's just not going to be optimal, right? So from A, which of the, like, there's two vertices next to it, which one is a shorter path from A? Yeah, so there's no reason to go to B because we might find a shorter path later. So let's just go to D because that is there's no way there's a better path to D. So we go to D. So here's a more specific thing. So yeah, we look at B, we look at D, and we're like, oh, D is like a shorter path. So let's just go to D. So now we look at these two options. So now from A to B, the path length is 3, and from A to E, the path length is 2. So which one do we want to go to? Yeah. So do you guys get that right? Like, if we go to B right now, there might be a chance that by going to E, we might be able to get back to B with like a length 1/2 thing and get to it in 2.5. So it's possible there's a better path to B, but there's no way to get to E in a better way, right? Because the only other option is to go to B, which is already 3, and there's no way to get back down to 2 after going to B. So essentially, we know that E is already the lowest it could possibly be, so we just go to E. Alrighty. And then we just repeat the process over and over again, and we see that B is now the smallest. We go to B, and then we go to C, and now we have all the shortest paths, right? We have, it takes a distance of 1 to get to D, right? We already knew that. It takes a distance of 3 to get to B, because this path is like worse, so that's not good. And then we know that it takes 2 to get to E, and then we know that it takes 7 to get to C. So essentially, that's how Dijkstra's work. It's pretty cool. Alright, this is our table of shortest path. So let me see. Okay, so basically this algorithm is really cool because all you gotta do is find the shortest path, which takes log n time, right? Because if you sort it, then you already know which the shortest path is. So this is a really fast algorithm for finding shortest path. It's pretty cool. Okay, so applications of shortest path. Digital mapping, okay? Literally Google Maps uses a variant of Dijkstra. Of course, there's a couple modifications because you don't want to like calculate it across the whole universe, like all the possible paths. That's kind of like not smart. But Google Maps uses a variant of this. And then social networking, obviously, if you want to find out how close two people are to each other. And then IP routing, right? Like, I want to send a message to Samuel. Like, I want to take the shortest path to get to him instead of going through some random routers, like, on the other side of the universe, which is basically what VPNs do, but, like, that's not, that's why they're so slow. They literally go to like, China or something and then come back. So, anyway, now let's talk about minimum spanning trees, okay? This is another application of greedy algorithms, and they are pretty darn cool. So essentially, it's basically finding a tree that includes all the vertices on the graph, but it's the smallest possible tree, right? Like a tree size is just defined by the sum of all the lengths on it. And essentially, greedy works. We just want to add the shortest length. Well, okay, hold up. Before I get to that, applications, okay? Let's say we wanted to find we wanted to find how closely related things are. We just find the minimum spanning tree on it, and then that basically tells us like the relationship between things. So it's kind of cool stuff. I don't exactly know the entire details of it, but basically minimum spanning trees are a really cool concept. So the first one is literally just Dijkstra's algorithm, but one-line chain. So instead of doing Dijkstra's algorithm, we want to add the edge that is shortest, right? We want to keep our MST as small as possible because the size of our MST is just like the sum of all the edges. So obviously, if we want to keep it as small as possible, we just add the smallest edge. Okay. But then the other algorithm is Kruskal's algorithm. So this one's a little bit more interesting. Basically, the idea is we keep adding the shortest edge until it's no longer a tree. So let's just do an example because that just explains it better. So here we go. Here's our graph. What is the shortest edge on this graph? Anybody? Yes, the one edge is the smallest edge on the graph. So we take the one, there's no problems with it, right? It's still a tree, we are good. There's no reason not to take the one. Okay, now what do we take? Who's the next smallest boy? Yep, 2 is the next smallest boy, no reason not to take him. Why would I not take 2? Let's just take 2. And then I accidentally took 3 too, so I don't know what happened there. But now what do we take? Yeah, we tried to take 4, but we got roasted because it turns out, like, then you gotta cycle in a tree, and trees with cycles are kind of nasty. And why would you want to connect these two vertices? They're already connected to each other. It doesn't make any sense whatsoever. So essentially the idea is we don't take the 4. So what do we take instead? Yeah, we take the 5 instead. And now, guess what? We are done with our tree. All of the vertices are connected. We took the smallest possible root. And all we did is do the best thing we could have done at that certain moment. So that's another really cool application of greedy. So I'm just gonna briefly go through this, but like you guys don't really have to understand this too much. But essentially, like, how do you know that the 4 connects 2 vertices that are already connected? How do we know those vertices are already connected to each other? Basically, the way it is, we just store what group each vertex is in. Okay, so that is what quick find is. So right now you can see that 0, 5, and 6 are all in the group 0. Makes sense. 1, 2, and 7 are all in the group 1, and 8, 3, 4, 9 are all in the group 8, right? So what happens if we wanted to connect these two groups? Let's say we put an edge between 1 and 6. What would we change in this array? We want to put them in the same group, right? So how would we make it so they're all in the same group?
You can change all the elements that are 1 and change them into 0.
Exactly. So you change all the elements that are 1s into 0s. Hooray. Okay, now why is this problematic? Anybody? So it's really easy to know what group something is in. You just look in the array. Easy. But like, how long did it take to actually bring two groups together? Anybody? Complexity? How much does it take? What happens if a group is n elements long?
Worst case is n.
Yeah, exactly. You could take n time just to make like concatenate two groups. And what happens if you have n union operations? Then that's like crazy. That's like n squared. So this is like kind of bad. So another thing we could do is quick union. Instead of converting all of these guys to point at the 6, right? We just convert the top one to point at 6. So if we wanted to find out what group 5 was in, we just go up the tree. 5 is in group 3, 3 is in group 0, 0 is in group 6, and hooray, we know that it's in group 6. But this is kind of bad because what happens if your tree gets like massive? That's not good. So essentially the cool thing that they do is instead of putting the larger tree under the smaller tree, if you put the larger tree above the smaller tree, then it keeps it very stable. So essentially it reduces the time complexity from n squared to n log n. It's pretty crazy. So that's basically like that's just like a bunch of cool applications of the greedy, and then like quick union does a really cool data structure. So if you guys have any questions, let me know right now. But we do not have a challenge for today. We have like a bunch of use to go problems on the competition website if you guys are interested in that. So any questions or anything about like any of the previous sessions? Aiden, is that a hand? Apparently not. Okay. If there are no questions, then we're basically done, so feel free to drop out, but I will stay if there's any questions. Anybody? No? Alright, I will end the meeting. Actually, well, the other people are probably going, so I will stay, but if you guys are done, feel free to drop out. Oh, shoot. God dang it. I forgot to send the meeting flag. I'm small brain, but whatever, I'll just... Okay, I'll just post it on the Facebook group like every time. Okay. Smallest brain, holy moly, how do I... Okay, whatever, it's fine.